I'm going to present you methods we've been developing during my PhD to automatically detect complex organic molecules toward hot cores using machine learning. And so, as previously mentioned this morning, hot cores are observed with interferometer and single-dish telescopes that provide us large bandwidth as high spectral resolution. And these instruments allow the community to detect more than 300 species now. And they also revealed that hot cores are rich, molecularly rich, and they can present a non-negligible abundance of complex organic molecules. So we have here an example of such spectrum extracted toward the envelope of a high-mass protostars. And to determine the molecular content of the spectra and the underlying physical parameter of the detected molecules, we have to do LT modeling and find the best fit for the model for each molecule. So here we have two examples for ethanol and acetone. So for the first species, we have quite strong emission with unblended lines, so the fitting can be quite straightforward, but that's not the case for acetone, where the signal is much more weaker and we have blended lines. So it can be much more difficult, and we have to do iterative fitting for each of the molecules, and it can take a lot of time when we have very rich spectra. So that's why we want to automate this kind of molecular detection and information extraction using machine learning. So in a nutshell, what we want to do when we have data cubes with machine learning is to determine the molecular content, and when we have the list of the detected molecules, determine the underlying physical parameter. The first step can be done through classification, whether it is molecule per molecule with each time a specialized artificial neural network for each molecule, or a multi-level classification. And the second step can be done through regression. But today, I will only talk about multi-level classification and the three main points that are needed to develop such a method, which are training data sets, the artificial neural network in itself, and the evaluation of the model performance. So now, that's not like other fields, some other fields that can do with only observations. We do not have enough fully analyzed millimeter and submillimeter spectra to build a reliable training data set. So we have to model the spectral emission of hot cores. And we would do this with LT models. We choose 20 molecules with some isotopologues on an early 3 millimeter band going from 80 to 115 gigahertz with a 1 megahertz resolution. In these molecules, we have small species having few transitions in the band, such as CH3N or CH3CH. And we have the most abundant COMs detected towards hot cores, such as AF glycols that can have thousands of transitions in the band. LT models have many free parameters, so we fix a lot of them, and we browse the column density, line widths, temperature of excitation, and the source size, so we can model quite very different type of environments. Also, as hot cores have very multi-physical stuff doing ongoing, so we have outflows, inflows, and they can affect the lines, a lot of morphology of lines. So we made the choice to hide some transition that can be impacted by such local physics. And so we do not have to do non-LT modeling. Once we have this collection of spectra, we can build our training data set, and we want it to be representative of the object we observe. So we try to boost to have the rich emission, but we avoid inducing bias by doing random combinations. Of course, adds noise that affects the detectability of each species, and we also add artifacts. So the neural network can learn that it doesn't necessarily have to interpret an unknown transition. When we have a synthetic spectra, we will build what we call targets. So it's a table saying if a molecule is detected or not. If the molecule is detected, we put a 1, otherwise a 0. And our detection condition is to transition at 5 sigma. And so we do this for all the species, for 4 million spectra, and we have our all training data sets, and we try to have a homogeneous representativity of all the species within the training data set. This dataset will be learned by an artificial neural network. So we made the choice to use a convolutional one because they have these convolutional layers that are able to extract information from the input data. So depending on their composition, they define what we call a receptive field. And so it can target small or large scale features. These features are then given to dense layers that will detect how to classify the spectra depending on these extracted features. And so when the neural network is trained, we obtain a model. And during inference, we obtain what we call a model score. So here, for instance, for AF vehicle, we would have a model score of 5.95. And also you can notice that we have an uncertainty, which is determined through Monte Carlo dropout. So it's a way to test the robustness between connections in the network by randomly switching off neurons. The model score can be used as it is, or we can calibrate it to have a detection probability. And we do this by doing a statistics based on a data set. And as we know, true and false detection, we can then determine a certain confidence based on model score. And everything of this is done with Siana, which is a framework developed by David Cornu. Once we have a model, we can test the performance of it. What is very useful are the receiver operating characteristic curves that are so the precision as a function of recall, and there are relations between true detection, false detection, and false non-detection at varying confidence threshold. And when we train a neural network, what we want to do is to maximize the area under this RSA curve. And here, for instance, we can see that for the molecule of CH2NH, the area under the RSA curve is lower than the other, so we expect a lower performance. This curve also allows to determine a certain detection threshold based on a given precision. So for a precision of 0.9, for the same species as before, CH2NH, we will have a threshold of 0.72. So if we have a model score above it, we can consider the molecule is detected. And we do this for each species, and it's also very model dependent. So we have to do it for each time we have a new model. What we observed is that the model is also very spectral line density dependent. So here we have the area under the curve, so which is a performance as a function of line density. So for spectral data set, for each spectra, we determine if molecule is detected or not, and if so, determine the performance. We do this for each molecule, and we can determine the mean value. And the overall tendency is that the performance increases as the line density increases. So we can determine a certain regimes of performance and adapt the detection threshold depending on it. So here we have an example for two line densities for 10 and 100 lines per gigahertz. And what we can notice is that for most of the species, the detection threshold will be lower as the line density increases, but for species such as CH3CCH or HT3N, that are so small molecules having a few transitions in the band, and it's linked to their performance because they have their peak performance at lower line densities. Now I will present you some tests we made on millimeter spectra. So here we have two examples. The first one is the spectrum of the protostar G320 observed with ALMA. And the second one is the spectrum of Sagittarius B2 Taurus, which is the richest region we know so far, observed with a 30-meter. On the right, we have, so again, model score obtained through Monte Carlo dropout and the detection threshold. For the first spectrum, 5 molecules are retrieved. And for the second one, 15 molecules are retrieved and 4 are not. And these are for species having weak signal, such as IF-ethylene glycol or FIT3H7CN. For the short-term goal is to use this model in the frame of the large program nascent stars. Timea already showed you these fields, which is the field of N53 of Cygnus 6. So we have here in the center two high-mass protostars from the same reservoir with MM1 on the right, MM2 on the left. And for spectrum extracted towards MM1, we have 6 molecules that are retrieved that has like a 5 sigma detection. And for the 4 other molecules that have a weak detection, the model do not detect them but 1. But of course, we do not expect the model to retrieve them because they do not encounter the detection condition. So the model was obtained with a certain frequency coverage going from 80 to 115 gigahertz. And so now what if we want to use it for a different spectral coverage? So for instance, if we take the substep 1 of EMIR going from 80 to 90 gigahertz and from 98 to 106 gigahertz. We have to adapt the task of the model through what we call transfer learning. So we will take the already trained neural network and make, again, few iterations of complementary training. Actually, only few iterations are needed to retrieve the same performance as for a full band. So now, what becomes very important, more and more important in the machine learning community is to interpret the so-called black box. And it's very important to understand the choices made by the model based on the learned features and determine some underlying bias. So different methods exist, such as saliency maps, line chap methods. But today I will only talk about occlusion analysis, which is the simplest one. And that's just a sliding window that will hide lines on the spectrum. And so we can really target the transitions that are important for the model to identify molecules. So here, for an example, so we have a spectrum in black. And so I show you here the occlusion score for ethylene glycol. And so we have occlusion score for on all the bands. And we have positive and negative score corresponding to correlations and anti-correlations. When we zoom in towards the maxima of this occlusion score, we can see that it corresponds to transitions to molecules of interest, because here we have the Hilton model of ethylene glycol. So now, to conclude, I hope that I convinced you that machine learning can be useful to automatically extract information from millimeter and submillimeter spectra. And so we want to use this model on a short term in the frame of large program nascent stars. And of course, we really want to go deeper in the model interpretation because it's very important to understand the behavior. And of course, we want to go towards regression. Thank you for your attention.